Make sure to like and subscribe right now. Yes, do it.
Hello guys, this is Rick from MathX, and today we're going to be solving the number 24 from the F is equal to MA of 2020. Now, this number 24, although having quite a terrifying appearance, is actually quite simple to solve. And as I'm about to show you, it requires basic knowledge in only two subjects in physics: circular motion and energy. But despite that, it's ranked as one of the highest problems on the test. So without further ado, I'll just show you how you could solve this problem. A mass M is connected to one end of a zero-length spring with a spring constant K. The other end of the spring is connected to a frictionless bearing mounted around a horizontal pole, so that the mass can swing in a vertical circle of radius r around the pole. The setup shown in the figure below. What is the vertical distance h between the center of the circular orbit and the axis of the pole? Assume that both the diameter of the pole and the rest length of the spring are negligible compared to r. Okay, so this problem has a lot. And even though it gives a diagram here, I think it would be useful to drawing our own diagram so we can get a better idea of what goes on. So here I've drawn a basic diagram of what's going on in the problem. I've labeled the center of the circle, the axis in which the spring is rotating about, and I even labeled the distance between them as h. Now, from here, it would probably be useful to label even more quantities. Since we know that this spring is zero length, that means that the distance from where the axle is to the spring will directly influence the force. So this length, the length from the axle to the lowest location of the spring, is probably important to note. So I'll label that as x1. Similarly, the distance from the axle to the highest point of the spring is also important to note, because these directly influence the force. So I'll label this as x2. Another thing useful to note, since it's in rotational motion, is the radius of the circular motion that it rotates about. So let's just label this radius as r. So we have a lot of information. Now let's think about how we can try to get h in terms of these three variables, so then we can understand what we want to find. Based on the diagram, we can see that x1 is equal to r plus h. And similarly, we can write x2 is equal to r minus h, right? Because both of these will have to add up to 2r. So subtracting x1 minus x2 would give us 2h. So what we need to ultimately find is x1 minus x2 by 2. And then that will give us our h value. So now we know what to look for, but now we need to obtain some method to get these values. So one way to do that would be by setting up as many equations as we can regarding the spring and the mass. So as I showed in this diagram, really there are two locations of interest: this top point and this bottom point. So I'll plot those out especially and label those with letters. Okay, so here is my updated diagram with the top and bottom points labeled with, I said originally letters, but I figured numbers are more appropriate since we labeled the distances with numbers. Based on the motion, we can set up a couple equations. First, we can try setting up the force equation for the mass when it's at position 1. So at position 1, we have the force of gravity and the spring force. And these combined forces yield a netward centripetal acceleration, centripetal force upwards. So the spring force upwards is simply, using Hooke's law, k times the displacement of x1 and then the downward gravity force is just mg. And this will give us our centripetal force, which is noted by the formula of mv squared by r. So our mass is easy, but we don't really have anything for the v at this point. So I'll just label this as v1 squared. And in this case, it's r because we're analyzing the circular motion about the center of the circle, not the axle. So this will give us an equation for the forces at 1. Now trying to obtain an equation for the forces at 2. We see in this case our spring force and our gravity point in the same direction. So we can write our spring force downwards, kx2, using Hooke's law, minus, or plus mg will equal to mv2 squared by r. So the signs are a little confusing, but I'm just using them relative to each other. Since the kx for the forces at position 1, since the spring force was going upwards and the gravity force was going down and the net force was still upwards, I just wrote kx1 minus mg equals to mv1 squared by r. For the second force, since the spring force is going in the same direction of the gravity force, which is the same as their net centripetal force, I just wrote everything as plus. If I set up a proper coordinate system, I could have just put pluses upwards and negatives minus, but I just saved a couple of steps by just keeping them relative to each other. Ultimately, they'll yield the same equation. So now we have all our force equations. And we just used spring force, gravity, and centripetal force equations. But ultimately, all we did was we added a couple new variables. So how are we going to use these? Well, another thing we can analyze is we can analyze the different energies at these positions. So this is our force equations, but what if we have a set of energy equations here? So underneath the diagram. If we take our bottom point to be Earth level, we can start setting up equations for the kinetic and potential energies. So the kinetic based on the law of conservation of energy, we know that the E at 1 is equal to the E at 2 because there's no external force acting on the system. We just have a spring rotating about an axle. Like there's no other force acting on it. So we know that the energy is conserved between these two, and there's no work done by anything. So we just need to analyze what's happening at position 1. At position 1, what types of energy are present? We don't have any gravitational energy because remember that's relative to our set ground, and here we set the ground to this, like to the level that 1 is at. So we can ignore gravitational potential energy in this case. But we're going to have spring potential energy, and we're going to have kinetic energy. So for kinetic energy, we get 1/2 mv1 squared. And then for the spring energy, we get 1/2 k displacement. So the displacement in this case is x1 squared. And this will be equal to the energy at 2. So 2 will have spring potential energy, it'll have kinetic energy, and it will also have some gravitational potential energy because since we set our ground to the level where 1 is at, 2 is significantly above that. So we're going to have to add the gravitational potential energy from the 2r distance in between. So first our kinetic energy, 1/2 mv2 squared plus 1/2 kx2 squared. My 2 is not coming out well. Plus the gravitational potential energy, which in this case is mg and the distance between them of r, 2r. So we put the 2 before and we put the r after. So now we have another equation. But here's the thing. We can actually solve for v1 and v2 in terms of k, x2, m, and g. And we can substitute these values we solve for v1 and v2 back into this equation. And that's kind of nice because now we have everything in terms of r, g, m, x1, and x2, and k, which is exactly what we want. We want to get rid of these v1 and v2 variables. So to do that, we just need to solve. We don't even honestly need to solve for v1 by itself. We can solve for v1 squared. Because anyways, we're going to substitute the square back into the energy equations. So we get v1 squared is equal to r k x, r by m, kx1 minus mg. And we can get v2 squared is equal to r by m times kx2 plus mg. Good. Right, so now we can substitute these squared values back into this equation. And just like that, we can see that these by m terms will cancel with the m's in the kinetic energy parts. So that actually simplifies it a bit. And then we can just go straight to just substituting the rest into it. So we got 1/2 of r minus k x1 minus mg plus 1/2 of k x1 squared equals to 1/2 of r kx2 plus mg plus 1/2 k x, oops, I messed up my k and my x, x2 plus 2mgr. So let's look at this equation. So we're left with this equation. And ultimately, all we need to do from here is just carry out some diligent algebra. And eventually we'll get an expression for x1 minus x2. So let's see how we can make that algebra a bit simpler. Well, the first thing we can see is that we have a 1/2 kx1 minus, we have a 1/2 kx1 squared, and we have a 1/2 kx2 squared, and we also have like these kx1s and we have these kx2s, right? So it would probably be in our best interest to try to group those together. So actually first we should try to distribute everything, so then it'll be easier to rearrange. But you know what? These fractions are kind of annoying. So before we even distribute, we can probably multiply everything by 2 to cancel out all these fractions. So first we do that. And we can, since we're multiplying everything by 2, we get this as 4mgr. Next we distribute. We got kx1r minus mgr plus kx1 squared is equal to kx2r plus mgr plus kx2 squared plus 4mgr. Good. So we see that we really only have like 3 types of terms. We have kx1 terms, we have mgr terms, and we have kx2 terms. So since we're trying to search for an answer in terms of x1 minus x2, we should group up the x1s and x2s and leave the mgrs on the other side. So we can do that by bringing all the mgrs to the right side and then taking all the kx1s and kx2s to the left side. So we got kx1 whole squared minus kx2 whole squared plus kx1r minus kx2r, and then we're adding mgr to the right side, which already has 5 mgr, so 6 mgr on the right side. And then this is looking a lot better. So here I've just rewritten the equation from the last page just cleanly on a new page because that page was getting really crowded. So as I was saying, now we have our entire thing in a much better form. We can actually start to factor the left-hand side, and the right-hand side is already looking pretty good. So the first thing we can identify right here is that we have a k in all the terms on the left-hand side, so we can factor that out. But even better, we also have an x minus 1 minus x, we have an x1 minus x2 term, right? Because this is just a difference of squares term. And difference of squares of x1 squared minus x2 squared is x1 minus x2 plus, or times x1 plus x2. And we just see, like, explicitly, this is just x1 minus x2. So we can factor out an x1 minus x2 term from these pairs as well. And then that will just leave us with an x1 plus x2 term as well as a plus r term. And that'll give us 6mgr. Yeah, so essentially all we did here was we just factored it using standard algebra. But here's the thing. Based on a diagram from down below, we see that x1 plus x2 is equal to 2r. So we can actually just cancel this out, and we get k times x1 minus x2 times, instead of x1 plus x2 plus r, we can substitute this back in with 2r, right? Because in our diagram, we had x1 plus x2 is 2r. So we'll just do 2r plus r, 3r. And that's equal to 6mgr. Now dividing everything else on the left-hand side to isolate x1 minus x2, we ultimately get 2mg by k. And that's good, because as we said here, that's what we wanted to find. But we have that h is equal to x1 minus x2 by 2. So in order to get the true value of h, we have to divide this value by 2. So we essentially get h is equal to mg by k. Which is answer choice D in this case. So this problem was not easy, but it was not impossible either. To do this problem, we just set up force equations and we set up energy equations, and we just used them and did a little bit of algebra. The key steps were to draw a diagram and then set up these equations. And then from there, it's just like any other, like not even physics problem, it's just a math problem at that point. So I hope you guys understood and saw that even number 24s and high-ranking problems on physics exams can often just be taken out with pretty standard strategies, like drawing a diagram and setting up equations. So thank you for watching, and I hope you enjoyed.